Okay, everybody, so this video is for section 6-2 from the pre-calc book. It's a lot on vectors again, and there are about 4 or 5 different topics that we're going to try and cover today in this. So the first one that we're going to do, we're going to talk about something called the dot product. And the dot product of two vectors, let's go vector here, 2 comma 5, and another vector here of 6 comma negative 7, something like this. The dot product means that you take the first two things in here and you multiply them together. So 2 times 6 is 12. Get your 12 there, and then you add the two parts right here. So 5 times negative 7, and that would be negative 35. And the dot product of these two things would equal negative 23. So a dot product is just a number. If you want to think of it this way, this could be A, B, C, and D, and it's A times C plus B times D, or horizontal times horizontal plus vertical times vertical. Okay? And you're like, well, what the heck does that mean? Well, this number is going to help us out in several different areas of it. And when we look at a dot product, if say if this was vector T and this was vector Q, then the notation would look like this. T with a big old honking dot and then a Q. Okay? So there's our first thing. That's what a dot product is. Now let's talk about where it comes into play, or at least a couple different places where it comes into play. So the first one we're going to do is, let's say that we had two vectors like this, and another vector that went like this. And if we put those together, these two things together, one would be here, like that. And then I put the other one, this one in this direction, this distance, going like this. We could find this angle, theta, in between these two things. So the formula asks for an angle between two vectors. And what we have to be able to do is get two vectors. So let's go 4, 7, and negative 6, 3, negative 6, 3. And I'm going to kind of draw those out right here right now for you. So 4, 7 looks like this. 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7. 4, 7's right up there. Again, has a horizontal part of 4, component of 4, and a vertical component of 7. Negative 6, 3. 1, 2, 3, 4, 5, 6, and 3 is over here. So negative 6, 3 looks like that. And it's not drawn perfectly to scale, but I'm hoping that you can see this. And you're knowing it's at least at 90 degrees or more. Okay? So what we're trying to do is we're trying to find what is the measure of that angle right there between these two vectors that are heading off in different directions. Okay, so the formula looks like this. It says we take the cosine inverse of the u dot v over the magnitude of u, and I think we've shown this before. If not, there's some notations for it. It kind of looks like absolute value symbols, two big long bars over it. Magnitude of u times the magnitude of v. Okay, so let's go ahead and do this math right now. Okay, so cosine inverse, that's just a trigonometric property that we're going to use, cosine inverse. And u dot v, so that's the dot product from what we had right up here. So 4 times negative 6 is negative 24. And plus, and then 7 times 3 is 21. So negative 24 plus 21, that's negative 3, right? So we'll get to that in a second. Magnitude of u times the magnitude of v. So magnitudes, right? That's square it, add it, root it. So that's 16 and 49, which is 65. So the square root is 65. And then here, 36 and 9, that's 45. Remember, don't forget a negative times a negative is positive. So these square rooted should always be the distances of those two things. And then we're going to multiply those together, right? Magnitude u times magnitude of v. So let's do that. I'm going to pull out the calculator right now, and hopefully you can see that here. So I got square root of 65 times the square root of 45, enter. So I got a 54.08 there. And negative 24 plus 21 is negative 3 over 54.08. And remember, I want to do cosine inverse of that. So here we go. You can see it. Pull this out of the calculator so you can see it right there. So let's do cosine inverse. So second cosine inverse of negative 3 divided by 54.08, and I hit enter and I get 93.18 degrees. 93.18 degrees. So let's go back to this, and you can see here that that angle, which we said was going to be close to 90 degrees, is in reality 93.18 degrees. Okay, so again, how do we work this out? I got this nice little formula right here. It says cosine inverse u dot v over the magnitude of u times the magnitude of v. So if you see that come into play and you're given two vectors, we're like, hey, what's the angle between those two vectors? You'll realize what you get out of it. Cool. Okay, so let's try another one right now. Here's the topic of something called orthogonal vectors. So orthogonal vectors are vectors that really are what we're going to call perpendicular. So the angle between them is 90 degrees. And basically what we're going to say is, when we start looking at these different forces, is any vectors that are orthogonal have no impact on each other. So like, say I was doing this, I was pushing something straight up into the air, and I ask you how far does it go left or right, and you'd say, well, it doesn't. Well, if I was just pushing something left or right along the ground, does it go up or down? And you'd say no. The reason is because vectors that are perpendicular have no force on each other. Okay, so how does that come into play with some of these things? We will know that the dot product of these two things, should equal 0. Okay, so let's try one of those things. Let's say one that goes straight up into the air. So would you agree that the vector 0, 6 has no horizontal part and has a complete vertical part of 6? And then another one that has no vertical part and a complete horizontal part of 10. So this has a force of 10 that goes to the right. This has a force of 6 that goes up. And we want to know what their dot product is. Well, if we do this, a times b, 0 times 10 is 0. B times d, 6 times 0 is 0. 0 plus 0 is 0. And you can see that those two things have a dot product of 0, which means there's no end result. And it doesn't have to be that they're vertical and horizontal. It could be that one of them is going at a 45-degree angle up, and one of them is going at a 45-degree angle from horizontal, and that still would have a dot product of 0. Okay, so let's try this one. So now we're going to look at, well, what happens? Let's say that I want to push a car. I want to push a car this direction, but I actually apply a force of it straight down the top. And I go, well, how much of this force that's going straight down, say I put 50 pounds of pressure on it this way, how far is it going to move it to the right? And the answer is it's not. It's not, because those two forces are orthogonal. My goal would be is to push it right there, right in the direction that I want it to go, because then every force or every amount of force that I put into this vector would get it going in that direction. However, it doesn't always happen that way. Sometimes the force is inefficient and we're pushing down on it, okay? So that means that this diagonal force is going to have some that's horizontal and some that's vertical. So what we're going to do right now is we're going to do something called projection vectors. And projection vectors means when I'm projecting one vector onto another vector, it's like how much of this thing right here, this thing that I got right here, is actually going in the direction of wherever my other vector is. This one happened to be an example of a horizontal one. Okay? So let's say I have a vector of 7, 6, and I want to project that onto a vector of 2, 4. Okay, so 7, 6 going on to a 2, 4. And I want to know, well, what's the end result? So this is what it kind of looks like. So a 7, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. 7, 6 is this big thing here, and 2, 4 is this one right about here. And I want to know out of this big long thing here, if I was pushing in that direction, how much of it actually ends up going in that way. Okay, we know that if it was perpendicular, right, to that thing like this, there'd be no effective force. It would end up being 0. But there's going to be something going in this direction. So what is that? That's the question. What is that? And we have a formula for that for projection forces, and it looks like this. That if you're going to project U onto V, and they just use U and V in the textbook, and you can read that too. U onto V, you do U dot V over the magnitude of V squared, which I know you do square it, add it, root it. So the squaring is going to kill the rooting in the end, but we still have to do it that formula, times V. Okay? So this is what we're going to do. So U dot V, so that's the top part of this. So 7 and 2 is 14, 6 and 4 is 24, 14 and 24 is 38. So I have a denominator of 38. And then the magnitude of V, that's this one right here. So I do 2 squared, which is 4, and 4 squared, which is 16. 4 and 16 is 20. Normally, to do the magnitude, I square root it, which would be the square root of 20, but then I square it again. So I really use 38/20ths. Does that make sense? And then I'm going to multiply that directly into vector V right here. You can see this. So multiply that into vector V2, 4. So I guess this is kind of what tells you this is how much I get in that direction. So 38/20ths. So I'm a handy dandy calculator right here. Let's go ahead and do this. 38 divided by 20. I get 1.9. So I'm going to do 1.9 times each of these things. And the reason is this original vector was really long, right? Let me clear that up a little bit, sorry. The original vector is really long, so it should have a pretty substantial effective force in that direction. So 1.9 of whatever this is. So 1.9 times 2 is 3.8. 1.9 times 4 is 7.6. Okay, so this is my new vector. Let's call this T. So if I was going to project, again, vector U onto vector V, like that, and we're going to call the end result vector T, I'd end up with a 3.8, 7.6. So 3.8 and 7.6, and you'll see that ends up being along the same lines as that. You can check the ratios. If you do tangent inverse of 7.6 over 3.88 or tangent inverse of 4 over 2, you're going to see that they end up going in that direction. Are we good? Does that make sense? Okay. So let's go ahead and try this one now. I think I can fit this at the bottom of this page still. So our fifth example is, let's say, effective forces. In the textbook, will go into some different. Ooh, that was weird. Didn't show up. The textbook will go into some different things, but let's say that I had a person, and this was a really slick surface. I had a person who set a box down on this inclined plane, and this inclined plane was inclined at 32 degrees, and the box itself weighed 150 pounds. Well, we know if we were to just hang that box in midair, we'd have to, on right here, apply a force that's exactly 150 pounds to keep that from falling down or keep that from dropping to the ground, right? And if I took that 150 pound box and I set it on the ground, and I said, well, how much force do I have to apply in this direction to keep it from going through the ground? The answer is nothing, right? All of it's just distributed that way. So the question is, these inclined planes, they kind of help us out. So if I was to put a rope onto this box and pull it tight at the same angle at what this this inclined plane was at, my question is, how much do I have to be able to withstand force-wise to stop this 150 pound box from sliding down this plane? And trigonometry works that out for us. Now there's some fancy things we can do with projection vectors, and sometimes we would do that in the normal class, but right now I'm just going to do it this way. You'll know that the only thing that affects this 150 pound box is gravity, and gravity is a vertical component, so we would need to know what that is. And now you can see if this is my 32 degree angle and this is my opposite side and this is my hypotenuse, opposite and hypotenuse is so sine. So I'm going to write this. Sine of 32 equals x over 150. And I'm going to go ahead and solve this equation right now. So here we go. So I got 150 times the sine of 32. And I get 79.5. 79.5. So x equals 79.5. Pounds of force. So that's what I would have to do. So like if I was, maybe this was an elongated hill and I've dug my feet into it and I'm holding onto this rope and this box is 150 pounds. And again, this is a slick surface, so there's no friction right there. How much do I have to withstand in order to be able to keep that from sliding down? That would be the 79.5 pounds. Okay? Okay, so 6.2 is almost done. There's a couple more problems in there. So again, so far we've talked about dot products and angles between vectors and orthogonal vectors and projection vectors and forces and stuff. Now we're going to talk about something called work done. Okay, so work done. So this one's kind of long in detail here. Here's example 6. How much work is being done in this situation? And the measurement in this situation is called foot-pounds. Foot-pounds. So I have a force of 20 pounds. So I'm pushing it with a force of 20 pounds. And I'm doing it in the direction of this vector 5, 13. Okay, so I'm doing it in the direction of 5, 13. So here's a little picture of what's going on. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 13. It's way up there. It's like this. Okay, I got 20 pounds of force going in that direction. Good deal? So it's not a perfect force, because our goal in doing this is to move an object from right here, from 0, 0, to 6, 0. Okay, so I should have, right, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. I should have tried to apply my force directly up, because that would be efficient, right? But unfortunately, this force is going a little astray, a little askew. It's off to the sides. I'm not really lifting the way I should. You know, Blazer or Meadows would be yelling at you, "You're squatting wrong." Okay, so we don't want to do a squat and push forward 8 inches. But this is evidently what happened in this case. But it's only 20 pounds, so I guess it's not going to hurt us on a squat. Okay, so what does it look like to be able to do this? Well, the first thing we're going to do is we're going to take the force over the magnitude of the vector, just like that, and we're going to multiply it to the vector, just like this. And this is, try and do all of these ones, right? This one right here. So that's my original vector. And then multiply that to where we want to end up, or the end direction of this 6, 0. Okay, so where's my force? My force is 20, just like that. And my magnitude of vector t, right there, my 513, 25 and 169, so 169 plus 25, I get 194. And then I got 5, 13, and I got 6, 0, and I'm doing the nice little dot product for that right there too. So 5 times 6 is 30, 13 times 0 is 0. So look at that. You can see, oh, I'm going to switch this. I'm going to switch this for you. I so wrote that down wrong back there. If you saw this, my apologies, I'm doing this without the example. This is from 0 to 6, because I drew the picture with having this go straight up instead of pushing it straight to the right. So let's do it with going straight up, which means that's got to be 0 and that's got to be 6. The only difference is the results right here. So 5 times 0 is still going to be 0. 13 times 6, 60, was that 78? Okay, so then I have 20, 194th times 78. So 20 divided by 194, enter, times 78, enter, I get 8.0 pounds, foot-pounds of work done. Okay, so again, a little oops on that. I wrote what I wanted to write first. I just draw the picture wrong, so changed it to it. This was trying to move it straight up, so that means the 6 had to be the vertical portion of it. So that all became 6's right there. Okay, so that's work done. This is 6.2 on vectors. Hopefully we're doing okay with this, and by the time you start watching this video, for most of you, we'll have done a lot of different things in the class. But I'm doing this video now before we've actually even gotten out of spring break. So I'm hoping that these are helpful. Again, take care. Do the best that you can with what we're doing. Stay positive with it. Ask me good questions. That kind of looks evil. Let's make that a little bit friendlier. How about that? Smiley face. Nope. No, it looks really kind of creepy looking. So, didn't mean it to be. You're like, just shut the video off. So this is Mr. Bellis, and take care.